Hello students, my name is Shashank Shekhar. So today is the fourth lecture of the chapter DNF block. In the previous class, we studied about the electrode potential. Now we will connect that electrode potential to the reactivity. Okay, because you know that if we're talking about reduction potential, that means we are talking about the reduction of that compound, or you can say the oxidation of that compound. Means change of oxidation state, or you can say in either way that change of number of electrons that is holds, right? So that is totally related to the reactivity also, because during a reaction we see those things only. So we can build up a direct relation between reactivity and the electron potential. Now talking about transition metal, so they are widely, means they vary in their chemical reactivity, and the reason behind that is you see that they have variable oxidation states, right? So due to this reason they have a varied reactivity depending upon the substrate that we are reacting it with. Okay, now most of them are you can say electropositive in nature because they react with mineral acids to liberate hydrogen gas, right? So once they form the, you can say once they react with the mineral acid, means they can be dissolved in mineral acid. So this thing should be clear. So if I am saying that if something is reacting with acid, then I'm also saying in a way that it is soluble in mineral acid. Clear? Okay. So this is about the you can say the reactivity of the DNF block. Now let us just move on to its more parts, right? Right, like when it will get oxidized, when it can get reduced. So if you talk about the metal that is in the first series means we are talking about scandium, titanium, vanadium, okay, chromium, manganese, iron, cobalt, nickel, copper. Okay, so we are talking about these elements. So talk about these elements, then out of these, only copper is more reactive and are oxidized by the 1 molar H plus solution. What is the meaning of this? So basically, it means that, so if you just take two chambers, so we am going back to electrochemistry here. So if you just take two chambers and in one compartment, if you just take the copper solution, right? Copper salt solution, 1 molar copper salt solution, and in the other one, if you take the 1 molar H plus solution, right? Then you will see that, okay, then you will see that the metal salt, the solution containing the metal salt will get oxidized, while the other one will get reduced. Okay, what does it means? It means that it has a, so you can say it has a reduction potential, negative reduction potential, right? Due to this reason, it is getting what? It is getting oxidized and it is not getting reduced. So this is very important that other than copper, okay, other than copper, all have a positive negative electrode potential, or you can say reduction potential, means they can be reduced in their standard state by the H plus concentration ion, 1 molar H plus concentration ion. But only copper is the exception, which has a negative reduction potential value. Is it clear? Okay. Okay. Now you have I have just revised this thing, right? We have seen this electrode potential comparison in the previous lecture also, but just to make a quick revision, I have just reminded it about the important point, that this is the important point here about copper. Now, E0 value of redox couple shows some interesting features. Like E0 value of M2 plus and M indicate decreasing tendency to form divalent cation across the series. So what does it means? So if you are moving from left to right, means the tendency to go to divalent cation, or you can say the tendency to get oxidized reduces, right? If you go from in a series from left to right, then you will see that the tendency to get oxidized reduces, or you can say the reduction potential value is increasing, right? Now due to that reason only it is uh, being able to, you can say, decrease its value, right? Clear? Okay. Now, E naught value for manganese, nickel, and zinc are more negative than expected from general trend, which respectively can be attributed to stability of half-filled D subshell in Mn2 plus. What does it means? It means that the E naught value, okay, means E naught value means the reduction potential that is required from moving from Mn2 plus to Mn, or you can say Ni2 plus to Ni, or zinc 2 plus to Z, zinc are more negative. Okay, they are more negative. More negative. Why is it more negative than from the expected trend? The reason behind this is that you see, after getting those two electrons, either they are being half filled or they are getting full filled. So here you can see for manganese. Okay, so if we just talk about Mn2 plus to Mn, then we are getting D5 configuration. Similarly, for zinc, if we are going from zinc 2 plus to zinc, okay, then we are getting D10 configuration, right? But for nickel, this is not the case. Okay, this is no relation between the, you can say, no relation between the orbital fulfillment, right? Here the factor is negative hydration enthalpy. Okay, highest negative hydration enthalpy. So whenever we dissolve Ni2 plus in, say, you can say, when we dissolve it in water, then a large amount of energy is released. Okay, now if you talk about Mn3 plus and CO3 plus, so they are the strongest oxidizing agent in aqueous solution because of highest delta H1, delta H2, and delta H3 value. Okay, while Ti2 plus, V2 plus, Cr3 plus are the strongest reducing agent. So what does it mean? So if they are Mn3 plus and cobalt 3 plus are the strongest oxidizing agent, means they can be reduced easily, right? They can be reduced easily. And why is it happening? Again, the same reason. If you just move from Mn3 plus to Mn, you will see what? You will see D5 configuration, right? Clear? Now, due to that reason, we are seeing that they are the strongest oxidizing agent. Now, the Ti2 plus, V2 plus, and V3 and Cr2 plus, so they are the strongest reducing agent. If they are reducing agent, means they are getting oxidized, right? If they are getting oxidized. Okay. So, what is the reason behind it? So when you are moving from Ti to 2 plus to higher oxidation state, then you are moving to noble gas configuration, right? You are moving to noble gas configuration, and same is the case for V2 plus and Cr2 plus. Okay, for Cr2 plus, we are moving to half filled d orbital, but not in this state. We are talking about the splitting one. Okay, so the thing is not given here. If you just oxidize Cr2 plus to Cr3 plus, then you will get a half filled d orbital in the lower set of the splitted orbital. So that is a different case. We'll study about it. Okay. Now this is about the reactivity. Okay. Now we'll move see some questions. So why is the highest oxidation state of metal exhibited in its oxide or fluorides only? So we have studied this, that especially oxides. Okay. So both oxides and fluorides are good in stabilizing the higher oxidation state, and the oxygen is even much more appropriate for that. And the reason is that they are able to form multiple bonds, right? Means in comparison to fluorine, the oxygen has a greater ability to oxidize the higher oxidation state, and that is attributed to the property of oxygen of making multiple bonds. And why is it so? Because oxygen and fluorine are more electronegative and can therefore pull electrons from the metal more effectively. So they are able to oxidize them in the higher oxidation state. Now, which is a stronger reducing agent out of these two? So if it will get oxidized by itself. So Cr2 plus will move to Cr3 plus, and Fe2 plus will move to Fe3 plus. So Cr3 plus is more stable, right? So Cr2 plus will be a greater, stronger oxidizing agent. See, and this is why, because after losing electron, it is going to half filled orbital in case of splitting. Okay, right? So if you have just heard about the splitting term, the d orbital gets splitted in the octahedral field, and that creates three degenerate orbital in the lower set and two degenerate orbit in the upper set. So as Cr2 plus move from Cr2 plus to Cr3 plus, then they are moving to half-filled lower set orbitals. For that reason, they have a greater reducing tendency, or sorry, oxidizing tendency than Fe2 plus. Now we'll talk about magnetic properties. So before moving to the magnetic properties, we must see that what are the type of magnetic attributes that can be shown by the same element. So first is diamagnetic. So by diamagnetic, and diamagnetic, they have a tendency to be get repelled by the magnetic field, means they are getting away from the magnetic field. Second is paramagnetic. So substance which are getting attracted by the magnetic field are called as paramagnetic. And the third one is ferromagnetic, so which are strongly attracted by the magnetic field. So ferro is related to the word iron, and we are saying it so because iron has a greater tendency to being attracted towards the magnet. Okay, right? As compared to iron, all are feebly attracted, right? Now, so the one which are strongly attracted are called as ferromagnetic. So talking about the magnetic property, so they come due to two reasons. First is the orbital contribution, and second is the you can say second is the spin contribution, right? So the first series element, so talking about scandium, titanium, and all, so they have they have a, you can say they have a negligent amount of contribution from the orbital, right? So it happens in this way. So whenever orbital, you can say it rotates. Okay, whenever orbital electron in orbital rotates, its angular momentum changes, and now due to that reason, it creates a magnetic dipole, a point dipole, and that is being attracted by the magnet. Okay, but for the first series, this orbital contribution is almost negligible. Now the magnetic moment is primarily decided by the unpaired number of electrons, so that is the spin contribution. So what I'm saying here is that for the first series, the contribution from the orbital is negligible, and it mainly comes from the unpaired electron. And the formula for that is root under n into n plus 2. Okay, so that this gives you the magnetic moment, where n is what? N is the number of unpaired electron, and what is mu? Mu is the magnetic moment in Bohr magnetron, or it is written as Bm. Now this, if you just calculate these values, then you will find that the experimentally determined magnetic moment is almost in a good accordance with this formula for the first series, because here the orbital contribution is negligible. Is it clear? Okay. So this is the list of the magnetic moment. So this is the calculated value, and this one is the experimentally determined values, right? So you can see very clearly that this is in a very good agreement with the experimental value. See, there is an error of 0.02 here. Okay, which is very negligible, right? Similarly for this also, for this also, for this also. So they all have very negligent amount of deviation from the experimental value, and this is directly calculated from this formula, which is root under n into n plus 2. So here we have taken n as 1 because you can see very clearly that it is Ti3 plus, which is having a 3D1 configuration. Means there is only one electron, and that is also unpaired. So n is equals to 1. For n is equals to 2, it is 2.84. For n is equals to 3, it is 3.87. For n is equals to 4, 4.90. N is equals to 5, 5.92. Then again, after moving to 3D5, we are starting to pair up the electrons. So one electron gets paired up. So we are left with 4 electrons, that is 4.90. Then again, the next electron gets paired up. Again, we have remained with 3 electrons, so 3.87. For 3D8, we have only 2 electrons. 3D9, or all 4 electrons are paired up except the last one. So we get it as 1.73. And at last, we have again 0 number of unpaired electrons. So this is having a magnetic moment as 0. Clear? And these are all the experimental values. So in this way, we have calculated the magnetic moment. Okay, clear? Okay, now next. Now, uh, let us see the color. Okay, let us see the optical properties of the transition metal. Now, transition metal have a very unique property to show variety of colored states. So depending upon the oxidation state in which it is being, so it gives a variety of color. And why this color why this color appear? Because so whenever we see a transition element, they are mostly present in a complex form in which there is a splitting of electron. Sorry, a splitting of the orbital. Now, what happens here? That whenever it absorbs energy, it goes in a higher energy state, and then it comes back and it releases some frequency in the form of energy. Right? Sorry, it releases some energy in the form of electromagnetic radiation, which falls under the visible region. Clear? Now, one very important thing that the absorbed and the emitted are complementary to each other. So we'll talk about this complementary color in the coordination compound. That what is the complementary color of different colors in the visible region. So this is about the color. So here is a photo of some colored ions. You can see that they can form a variety of colors. So moving on to light pink, yellow, okay, green and blue, etc. Right? Now complexes, as I've told, they can form complexes. So the example of few complexes are FeCN6 whole 3 minus or FeCN6 whole 4 minus. Now in this case, the type of bonding that is seen is coordinate bond, and that is different from the normal bonds or the covalent or the ionic bond that we have encountered till now. So we'll discuss briefly about more about this thing in the coordination compound chapter. So here again we have two more examples. Now, this is due to comparatively smaller size of metal ions, their high ionic charge and availability of d orbital that they are able to form the complex. So, the reason behind the complex formation is because they have a very small size, okay, and their ionic charge, high ionic charge and availability of the d orbital. Next is catalytic property. So, we have seen that they have a variable oxidation state due to the availability of d orbital, and due to this variable oxidation state, they are able to do the catalytic work. And what is catalytic work? So in catalytic work, basically see the transfer of or acceptance of electrons, and since it can move to various of this oxidation states, so it is capable of doing so. Now the activity is ascribed to their ability to form multiple oxidation state. So same thing is written. So due to the its property to form multiple oxidation state, it can form complexes. Clear? Okay. Now, examples of the catalytic property. First is vanadium oxide. It is used in contact process. Then we have iron. It is used in Haber's process. Again, we have nickel, which is used in catalytic hydrogenations. Right. Now, formation of bonds between reactant and a molecule. Reactant molecule is the atom of catalyst surface. Catalyst at a solid surface involves the reaction. So, what do you mean by this? So, whenever it is mostly used as a metal surface for what? For gaseous reaction, because on the metal surface both the reactant and the product are absorbed, and due to that their proximity increases, means they are more closer to each other, and if they are more closer to each other there is a chance of reacting, right? So by absorbing them both on the metal surface, and in addition to the proximity factor, they also increase the activation energy, sorry, not the activation energy, yeah, they also decrease the activation energy, right? They decrease the activation energy required for the molecule to react. Clear? Okay. So, so once it is gets absorbed, so as I have told, it decreases the concentration. It also weakens the bond between the reacting molecules. So because they have formed bond with the metal, and metal has formed bond by reducing the number of electron in the bonding orbitals. So therefore, it is reducing the what? It is reducing the number of bond orders, and therefore it is weakening the bond. Now transition metal can change their oxidation state, and due to these three reasons, they are acting as a catalyst. So here, for example, the iron in the +3 oxidation state act as a catalyst for the reaction that is given here, in which the iodine is getting oxidized where the sulfur is getting reduced. Clear? So this is the catalytic activity it does. So first of all, it converts, it reacts with I minus to give I2, okay, and plus in addition to that, it reacts with S2O minus to give Fe3 plus. So you can see that the number of Fe3 plus ion is same. If you just add both of this equation, it will get cancelled out, and they will see that you will see that there is no activity of the catalyst in the net reaction, right? So this is now this we'll talk about interstitial compound. So we'll brief it more in the upcoming lecture. For now, just I'm giving a quick introduction to that. So what happens here? So small atoms like hydrogen, carbon, and nitrogen. So they get trapped in the metal bulk, right? And due to that reason, we see an interstitial compound. Means in on the between the metal ion, between the metal atom, there is some gap present, and in that the small ions like hydrogen, carbon, nitrogen, they get trapped, and due to that reason, they form these type of compounds. You can see that they are in some cases they are also not whole numbers. So here 0.56 and 1.7 because it is not defined well. It is just getting trapped there. So if I talk about the property of an interstitial compound, they have a high melting point because now they are having a more compact structure, and they are was also very hard, right? Now talking about the conductivity, so it retains its metal conductivity and it remains chemically inert. Now we'll talk something about alloy also. We'll talk in more description in the next class, but for now just look at it and get an idea about what is alloy. So alloy is basically a blend of two or more components. Now they are homogeneous solid, means the concentration is equal throughout the alloy, and the atoms of one element are distributed randomly atoms of the another. So what do? We take two metals and just metals, or you can say elements, and just make a third compound out of it, in which they are close in the two elements are closely packed. Now transition metal form alloys like ferrous alloys, which are formed by the chromium and vanadium. Now if I talk about the non-transition metal alloys, then we have brass and bronze. So next is disproportionation reaction. So what is disproportionation reaction? So in a disproportionation reaction, a same metal will get splitted, or you can say they will get reduced or oxidized to two different oxidation states. Here you can see that manganese can disproportionate into +7 oxidation state, means +6 to +7, and simultaneously it can get reduced to +4 also in the same reaction, and it happens in the acidic solution. Clear? So last question: why Cu plus is not stable in aqueous solution? Because it undergoes, again the reason is because it undergoes the disproportionation reaction and forms Cu2 plus and Cu metal. So see, Cu plus is getting oxidized to Cu2 plus, and at simultaneously it is getting reduced to Cu copper. Okay, so due to this reason, due to the disproportionation of the Cu plus oxidation state, we do not see a stable Cu plus in the dissolved state. Clear? So this is the reaction that Cu plus is going to Cu2 plus and Cu. So this reaction is also catalyzed by the presence of water molecule, which can donate electron to the Cu plus ion and help to reduce it to metal. So this is catalyzed by the water. Okay, because it helps in facilitating the number of electrons. Clear? So this was for today's lecture. We'll talk more about DNF block in the next lecture. Thank you.